Hello. For the objective of this assignment, the first objective is to analyze the circuit by knowing the direction of current flow and also to draw the correct circuit with correct values of impedances at loads and transmission line. Figure shows the circuit for this assignment. Second objective is to understand and solve the calculation. There are many methods to solve the calculation. One of them is Ohm's law, which is V equal to IR. And we also need to know the basic knowledge of parallel and series circuit for the calculation. We also need to calculate the power triangle, which consists of complex power, apparent power, and real power. The two figures show the power triangle. The left figure is the power triangle before the power factor correction. Meanwhile, the right figure is the power triangle after the power factor correction. Power factor correction is needed to improve the system by having new value of capacitor. The third objective is to be able in handling simulation. Simulation is used to prove the calculation. Based on the table, there are two columns which consist of calculation and simulation value. The calculation value is almost the same to the simulation value. This proves that the calculation is correct. And the last objective is to know the application and benefit of the power factor correction in real life. The benefits of power factor correction in real industry is reducing the electricity charge and also reduce the heat in cable alternators and transformers, which will prolong the lifespan of such equipment. That's all for the objective.
Assalamualaikum warahmatullahi wabarakatuh. My name is Hasimah. For the calculation, we're gonna calculate the current, voltage, and impedance across load by simplifying the circuit. So, based on the information given of value of power at each load, we can calculate the impedance by using formula of S equal to V square over Z conjugate, since voltage drop at Z3 is given. So, for at load 3, we can use formula of S equal to P plus JQ. By applying Ohm's law, we also can calculate now I total line and voltage total line at each transmission line after Z total line is obtained. Same case to load 2. Same principle is applied for load at Z2 and Z1 as long as we are able to calculate the total voltage at each line, where voltage total for line Z3 is equal to voltage total of line ZC and voltage drop at Z3. So in this case of load 2, we have to simplify the impedance by parallel impedance. So for this case, we have to multiply Z. We have to parallel Z total line of 3 and 4 with Z2. By parallel them, we can one new value of impedance, or in this case is ZY. And continue using Ohm's law, we can obtain I total line and voltage total line. So this is the circuit after the impedance of Z total line 3 and 4 is parallel with Z2 and obtain of ZY. ZY will be in series with ZB. So next, we calculate the impedance, current and voltage at load 1. For the calculation of load 1, using formula of S equal to V square over Z conjugate, and repeat every step of calculation at load 2. So this is the simplified circuit after the Z total line 2 and 3 is obtained. So for AC main supply voltage, we can use Ohm's law and we have to understand KCL. So for current total, we can analyze by adding I load 1 and I load 2 and 3, since I in is equal to I out. So in this case, I total is equal to I total line 2 and 3 plus I load 1. The voltage supply can be obtained by multiplying current total with Z total. So we obtain the voltage supply. So this overall circuit that we analyze each current using KCL and obtain the current at each line and at each load. So for the calculation of real power and reactive power. Real power and reactive power, for this we use formula of I square RMS of current across the load or line where power is measured. For reactive power Q is we can using the formula of I squared over X. Next, power triangle. Power triangle can be obtained by calculate value of S, where S is equal to Vs multiplied by current total. From S we can obtain the value of P and Q. Using value obtained we can construct a power triangle. Next, for designation to improve the system. So the power factor given is 0.98 lagging. We have to calculate the QC by using the formula of Vs squared over Xc, and we can obtain by using formula of Q equal to P tan theta and QC equal to Q old and Q new. So this is the value of Q new and the value of P. This is the value of power, real power, reactive power, and apparent power of new after power factor corrections. The power triangle after power factor correction. So based on the picture, we can see the value of Q old and Q new. From value calculate, power triangle is created, and power factor correction is proved to help to reduce power loss since Q new obtained and S new obtained less compared to Q old and S old value. So that's all from me. Thank you.
Alright, so let's start with the presentation. So I'm going to present about the knowledge and simulation, but before that I'm going to show you the PBL that we need to design. So in this simulation we need to design this circuit, as you can see in the screen, and then you need to open your multisim. So I have already designed it, and here we go. So for the first one, we need to show you about the current flow in each load and the total current supplied by the source. So it is the current flow in each load. Okay, here we go. So wait for a few seconds. Alright, here we go. So this is the circuit. First of all, you need to design exactly as you design in this circuit, and you need to what we call that, transfer it into the multisim. And then this one is we need to find for the current flow in each load and the total current supplied by the source. So I already put the ammeter for every load. For this is load 1, load 2 and load 3. So this is the ammeter 1, ammeter 2, ammeter 3, and the total current supply for the ammeter. So we just need to run it to get the answer. Wait, okay, here we go. So as you can see, the IPR2, so it is here. It is the total current of the circuit, 844.07 with a phase angle of 4.06272, and it goes for the load 1, load 2 and load 3. Here load 1, load 2 and load 3. So that's it for the current flow in each load and the total current supplied by the source. So next we go for the real and reactive power losses at the transmission line. Okay. Get back. Okay, so this is the same circuit but different measurement. So now we need to find the real and reactive power at the load, at the transmission line. So the important part about this thing is when you design this circuit is the positive and negative terminal for voltage, and you also need to know the direction of the currents when you put this one, the ammeter, in the circuit. After you decided all the voltage meter and the ammeter, just need to run. So this is the wait, before that I already put the formula for the real and reactive power. So this is the formula. It is V times by I conjugate, as you can see here. So it is the same with the other transmission line. This is transmission line 1, transmission line 2, and transmission line 3. So this is the result, the real and real and imaginary. So that's it about this. Next we go for the total apparent power and real power. Okay, so for this one you need to put the voltage meter at the voltage supply at here and here. This is a positive probe and this is negative probe, and the ammeter is also applied as the same things. You put at the after the power supply, and then you need to put it here at the ammeter. So same like this, you just need to start it and calibrate. So this is the current, this is the voltage, and this is the apparent power, total apparent power. So this is the real, this is the imaginary. 230.425 and imaginary is 78.79. Okay, so this is it. Next we go for the measure the correct value of the following to prove task 2 after PFC. PFC is a power factor correction. So we need to find the new real, reactive, apparent power and the power factor after improvement. So okay, just okay, wait, okay, so this is the design. It is same. So after the calculation we have decided to put 1.187 millifarad to correct the power factor to 0.98, which is the right capacitor according to the calculation. So we just need to calibrate it, to simulate it. Okay, after then this is the result after the new power factor change, power factor correction. So the real power is gonna stay the same and your imaginary gonna change a little bit to follow the 0.98 power factor. Okay, that's it from me. Thank you.
Okay, Assalamualaikum warahmatullahi wabarakatuh, and hi, So now we go to the next part, which is result analysis. Alright, so here is the table showing that the data of calculation and simulation of our findings, and as you can see, there is impedance, voltage and current. So if you observe closely, we can see that the difference between all those variables is in between plus minus 1. So I take an example, I total calculation and I total simulation. If we subtract between these two, IS sim minus IS calculation, we can get in the answer is 0.46463, which means it is still in between plus minus 1. And this is because we ignore some decimal point. Unlike the simulation, we took all the decimal points, so there might have slightly difference in the results, but it is still the same. It still can be reconsidered. It still can be considered. Sorry. Okay, so next is table of real power and reactive power. This still is also the same like before, table before. The data between those two is still in between plus minus 1. For example, this real power for P line 1, 2, it is 9.963, while this one is 9.97447. It is still below 1 plus minus 1. Okay, so the calculation is done by solving the circuit using basic knowledge of circuit theory and network analysis. We apply the AC analysis that we learned from class into the system to calculate all those data. So, and it is proved by perform the simulation using multisim. And result obtained from calculation is based on theory and being proved in real station simulation. So we can say that the result obtained from calculation, which we use theory as our guide, has been proved by using simulation using multisim. So next we go to the power factor correction. The table shows power factor before PFC and after PFC. It is listed in calculation and simulation. So it has apparent power, real power and reactive power. Alright, as you can see, if you look closely, the real power remain the same for before and after PFC. Okay, I took the simulation example, 230.42573K and 230.42587K for before and after PFC. But for reactive power, it changed, it dropped, it decreased. And this is because in PFC we add capacitor. So capacitor does not affect the real power because real power is affected by resistor, but for reactive power it affects. Okay, addition of capacitor cancel the inductive effect of load, and also vice versa. If we add inductive and it will cancel the capacitive, but this circuit is in inductive circuit. We can see also the current is decreasing because the power is decreasing. So behavior of the system before and after PFC. For both, I total is lagged by Vs, and for before PFC is by 18.665 and after PFC is 11.29. We can see that the degree is decreasing, and this is because we already cancel a bit of the inductive effect in this circuit, but it still cannot overcome the inductive value because it is an inductive circuit. It can only lower the degree, so it can go up close to the 1.0. Okay, so conclusion and application. We all know that PFC has been widely used in various sectors such as heavy industries like factory and big company, and big plant. So PFC helps by reducing the reactive power and current carried by a system. It allows the system to carry new load, and it will affect the cost of the company. So it will save the cost of upgrading. The company no need to upgrade many things. And PFC helps improve our daily life, increase our load carrying capabilities, and reduce power system loss. Because we aim for 1.0, but we still can get 0.9. It is good enough. So the conclusion is we have achieved our objective. We have analyzed the circuit using AC analysis method. We also have calculated the voltage, current, impedance and power for this system. we also apply the power factor correction and run in simulation. That's all from me and us. Thank you.